The first topics we're going to be talking about in Chem 105 are going to be really just looking a little bit more carefully into the way gases behave, and then we'll work on into how liquids behave, and then we'll eventually work into solutions, sometimes of liquid in a liquid in a gas, or a liquid in a solid. But for now, we have to start off talking about a pretty important concept called kinetic molecular theory that has everything to do with these little particle diagrams that we talked about in Chem 104. So just as like a kind of, I don't know, a reminder, I guess, of some of the things we talked about, there's some really good animations out there that I have found, and this is one of them. This is from University of Colorado. And in this, you'll notice that we're now talking about gases. So this is kind of an idealized representation of what these little gas particles could do. You'll notice that in this particular case, these are all neon particles, and it's held at a very particular temperature. So one of the things that you'll notice all these guys are doing is they're really just all bouncing around, right? Sometimes off of each other, sometimes off of the walls. You'll notice also that these things are all kind of moving at different speeds. But what we're going to eventually talk about is that the speed that these particles are moving at actually has something to do with the temperature. And so what we're going to be kind of developing over time here is just kind of to add a couple of important considerations into these little particle diagrams. So just to make sure everybody's kind of starting on the same page here, you could just as easily have some sort of liquid sample of neon if you got it cold enough. And you can see here in the liquid phase, these things, they're jiggling around a little bit and still bouncing off of each other, but it looks a lot different than in the gas phase. One of the most important things that we're going to be talking about for gases is that they expand to fill their containers. And so you can see, and we've got everyday experience with this, if you just imagine like a cup of water or something like that, is that it kind of stays at the bottom of the glass and sloshes around a little bit. But the second you turn that thing into a gas phase, it expands to fill the room that you're in, otherwise known as evaporation. And then, of course, we could talk about, some sort of solid, and you notice that there's a little bit of vibrational energy there, but not too much. So we're going to be starting the term talking about gases. Here we have my representation of every time I think of gas, I can't help but be 5 years old. So the only thing that's important is I'm the only one allowed to do fart jokes. So let's kind of develop some of these ideas of kinetic molecular theory by going back to kind of a more involved animation over here. You guys should all feel lucky, because if we were in class right now, what you would be doing is you would become a gas particle, and you would have to bounce around the room just like these guys right here. And what we're going to be doing is we're going to be talking about these tenets or postulates of kinetic molecular theory. And if you kind of understand this model and what's happening right here, and what you would be doing if you were in a classroom and bouncing around like an idiot, you would understand all of the tenets of kinetic molecular theory with just a couple of little fine-tuning, vocabulary words from me. So one of the first things you'll notice is that when we look at the postulates of this kinetic molecular theory, there's a couple of things that have to be true for something to truly be operating under these tenets. Let's run through a few of these postulates. So first one is that every single gas sample is actually matter that consists of tiny particles, right? Well, that's not hard. That's something we already talked about in Chem 104. There is one kind of, like I said, fine tuning that we have to do, is that under the kinetic molecular theory, we have to assume that these particles occupy no space themselves. And what I mean by that is that each one of these little tiny spheres that we see bouncing around here, like that slow guy right there, he is actually itself occupying no space, right? In other words, it's just a single point in space. Obviously, that's not true. That's not even true of normal atoms and molecules. But under these postulates, that has to be true, and it greatly, makes our lives simpler. And so what we're kind of building our way towards is this idea of ideal gases. And the good news is that most gases under conditions that they do in fact behave ideally, right? The total volume that this entire sample of gas occupies, which you can see is this like giant square or rectangle or whatever it is. So relative to that, these little tiny individual little balls of matter are incredibly small, right? They really occupy no space. And of course, if we made this container bigger, that would be even closer of an approximation. So what we're going to assume here is that that these particles occupy no space, and you can also see that they're just constantly these little tiny, in this case, atoms that are bouncing off the walls. Of course, we could also have imagined these guys being waters, right? And then they just look like a whole bunch of little Mickey Mouses, a bunch of H2Os bouncing around. But overall, that's the most important thing to recognize about KMT theory if you're a cool person and you want to just use acronyms. Another thing that is true is that they are in constant random motion, right? And so you can see that there is not too much, I don't know, anything ordered about the motion of these things. The important thing is just like if I had a ball and started bouncing it around, right? Eventually, as that ball got heavier and heavier, I could break windows with it, right? The same is true here, is that because these particles are moving, they have the energy of movement known as kinetic energy, right? So there's kinetic energy right there. And so that's another postulate that we should keep in mind, that all of these samples of gas, even though we can't necessarily see these little tiny point charges, right? The fact that they are in fact moving says that they have some sort of kinetic energy. Another important postulate of this theory is that these particles do not attract or repel each other. And I call this the pool ball analogy, right? All of these things, right, they're really just bouncing off of each other, kind of like pool balls. And it's important that we assume that they don't attract or repel. But the problem is that if we were, actually these molecules, let's say if these were H2O molecules, we would actually see that that is not true, right? And so in this kinetic molecular theory, where we're kind of working towards the way that a gas behaves, is we're not allowed to imagine that those things are attracting or repelling. And actually, even in the case of water, if you imagined heating up steam to like a really high temperature, for the most part, the interactions that those waters are experiencing between two particles is really not significant, right? They're just moving too damn fast. And of course, if you imagine something like helium that doesn't have like a separation of positive and negative charge, helium's basically this little tiny sphere that doesn't really have any reason to interact with any kind of heliums, right? Well, that is a much easier approximation to make, that these particles don't attract or repel each other. They really are just little tiny pool balls constantly bouncing around with a bunch of kinetic energy, and they themselves occupy no space, right? It's only the collisions with the container that ultimately, kind of define what space that they occupy. The next postulate probably won't surprise you, but as you increase the velocity of these, as you increase the temperature, the velocity of these particles increases, right? So what we're going to do here is just play around a little bit. We're going to take a look at the temperature right there, because it turns out that temperature is really just a measure of the average kinetic energy of all these particles. So watch what happens. Not surprisingly, when I heat this thing up, obviously the temperature goes up, but you'll notice that these collisions become more and more constant. The particles start to move around more and more and more. And it turns out this is exactly what happens when you heat a sample of gas, right? That's, there's not much we can say about that other than the fact that I guess it's probably important that we talk about the fact that some particles are moving like crazy, right? Like, look at that guy. Some of them are moving pretty slowly, but what is true of a constant temperature is that they overall have the same average kinetic energy, right? So for instance, or let me show you another graphic. Here's another way of thinking about this connection between temperature and the velocity of particles, and ultimately the kinetic energy of these particles. Because what you'll see here is there's this graph where we've pretty much listed out all of the speeds that are possible for these particles. And then this graphic kind of counts up the number of particles of that particular speed. So for instance, right now, we see that the majority of particles have a speed right around whatever this value is. And of course, this is a dynamic sample, so there's a lot of things changing, but you can kind of see that there's pretty much the same amount of particles with a constant speed. And you also see that the kinetic energy, right? All these different particles have different amounts of kinetic energy. So what I'd like you to see is what happens as I heat this sucker up, right? And I'm going to notice obviously an increase in temperature. And what we'll notice is that the average velocity, or in this case speed, of these particles should go up. And watch what happens to a couple of these graphs. So now it's pretty obvious that we've got these particles moving around a lot faster. The temperature went up quite a bit. You'll notice that that average speed also went up quite a bit because that velocity has everything to do with temperature, right? The average speed and the temperature are really talking about the same concept. You'll notice that as I heated this sucker up, that there are now a whole bunch more particles out here that have much faster speeds. And also the kinetic energy profile here, you can see that like the individual kinetic energies of all these particles kind of smeared out into some of the higher regions here, whereas before it was really centered all around these kind of low kinetic energy areas here. So what we're kind of working towards is this really kind of a junction of physics and chemistry, right? I'm a physical organic chemist, which means that I'm really into kind of combining physics and chemistry because I'm a sick person. But this is the kind of stuff that that makes our hearts go pitter patter. For us, all I want you guys to recognize are these different postulates of the kinetic molecular theory. And keep in mind that everything we talked about, whether it's a gas, a liquid, or something even that's happening right in front of us, that all of these things are really just a whole bunch of different little particles that are all interacting in a certain way. And so this is something that is true of gases. One other thing which we should mention in terms of the final postulate of kinetic molecular theory is that all of these collisions are perfectly elastic. In other words, there are no the energy doesn't bleed from the system. This turns out to be a pretty major assumption, one that will kind of develop over time. But these are things that I really want you guys to be thinking about as we start to talk about gas laws, because it really makes things a lot easier. Another concept that's going to be super important to us as we continue to study gases is this idea of pressure. And as long as you have this kind of particle diagram in your head, it turns out pressure is very easy to understand. Right? We could be physicists and say, oh, it's force per unit area and things like that, right? But the important thing is to recognize is that where is that force coming from, and what does this mean, right? Like on a gut level, what is pressure? Well, for that, what I'd like you to do is watch what happens as I pump gas. By the way, these are pretty slow moving gas particles here. I want you to keep an eye on what happens to the pressure, right? Let's just do 1 or 2 pumps here. You'll notice that I just put a whole bunch of gas into the container, but you'll notice that the pressure only goes up when these things collide with the side of the container, right? And so notice, see, the more collisions you have with the sides of this container, the higher your pressure gets. And of course, eventually it'll just kind of equilibrate. But watch what happens, and this should kind of make sense to you. As I put more and more gas in the container, there are more and more collisions, right? That means that there is a higher pressure. So this idea of pressure, right? Think of your tires, right? As you increase the amount of stuff in your tire, your pressure increases, right? Because you've increased the number of these little particles that are constantly elastically bouncing off the edges of your container. And what other things can you do to make be more frequent and more forceful collisions? Well, turns out I could heat that sucker up, right? When we do that, the pressure would probably go up. And in fact, it does. right? And that's crazy or not, right? If you understand this particle diagram, you understand exactly where pressure comes from, right? When we feel pressure, right? Like if you were to, go way up in the mountains. One time I had a problem where I destroyed my eardrum and I went really high up into the mountains on a climb, and I was in excruciating pain, right? And it has everything to do with the amount of pressure that my body was putting on the insides of my ears, right? That pressure was kind of trying to really, escape out of my ear like it would normally do, except that I screwed myself up and I couldn't equilibrate my pressure, right? And so this kind of thing, gives you an idea of what, atmospheric pressure really is. It really is like the weight of all those particles kind of pushing down on you. And as you go higher and higher in the air, right, there's less and less air pressure because there's less and less collisions with, the side of your body. The air is exerting less of a force per unit area where you are that area. So this is kind of an, just a real brief introduction to some of the concepts that we'll be going through. I am going to have one other kind of, video or section of this video for you guys to watch having to do with how we're going to actually use units of pressure, and also how to, as kind of a review of some of the dimensional analyses techniques that'll become important to us.